Hi, it's Tommy, and I'm going to be talking about my answers for the isomorphism assessment. So question one, what is the height of the corresponding 2-3 tree? Basically just drew the 2-3 tree by combining the nodes linked together by a red edge, and here it is. And as we can see, the height is 2. How many values do you need to add to the 2-3 tree to cause the height increase? So let's see what the best node is. What the best node is when you're trying to add trying to add 1 to the height of this tree. Well, there is a 2 node right here. So if this becomes a 3 node, then um one of the nodes gets promoted like this, and this connects to the very top node of the tree. That's after we go and add 1 extra element to this node. And now if we add 2 more, one more will be promoted to here, but then this node will be overstuffed, which would make the top node overstuffed, which would give us, and when the top node is overstuffed, it will promote one node above it, which would result in the entire tree um having a height increase. So we need to add 1 here, and then 2 here. So that would be 3 values that we need to add. And the next question is, how many do we need to add to the LRB tree? Well, in the LRB tree, all we have to do is just say um add a node right here, and that would be a height increase. So all it takes is one value. And in question 4, what happens when you add a new element that is greater than all the new other elements? Well, in that case, we would have to add a new element here. Right here. So this would be a new element, but since the red links have to be leaning left, this would break the invariant. So we would have to um rotate these 2 nodes to make the red node lean left. So in the end, we're gonna add a red edge paying off the rightmost branch, which is this branch right here, and rotate left on this node. So basically we're rotating this node to the left to make it so that the red node, so to make these nodes switch places, and the red link would be leaning left as required by the LLRB tree. Okay, so the next part is quicksort, and the first question asks us for valid partitions. And to do this, all we really need to know is that what makes a valid partition valid is all of the elements before the pivot is less than or equal to the pivot, and all of the elements after the pivot are greater than or equal to it. So as it turns out, these 3 are the only ones that fulfill this condition. For the last one, we have a 4 after the pivot 10, which shouldn't be there because everything after should be greater than or equal to 10. Now, the question 2 is asking us for the best case runtime for quicksort. So let's think about what the runtime for quicksort depends on. The only choice that we're really making is the pivot choice, and that's the only thing affecting our runtime. But how does it really affect our runtime? Well, if we look at every time we choose a pivot choice, we're really making everything before everything. We're making sure we're choosing in pivot such that everything before is less than, everything after is greater than. And once we choose this pivot, we're going to choose a pivot in the before section so that everything here is before and everything in the other part is also fulfills this property. So every time we choose a pivot, it's really like fulfilling a um, binary search tree property, which and the pivot itself are like the nodes. So every time we go down and choose smaller and smaller um, partition partition perform the partition out operation on smaller and smaller sections of the array, we're really going down a binary search tree until all of the elements are after they are chosen as pivots, all of the elements fall in where they should be in a sorted array. So for this kind of quick sort algorithm to complete, it's really like going down a binary search tree. And we know that in a binary search tree of n elements, the amount of levels is log 2 of n. And since each time we choose a pivot, we have to run a linear time partitioning algorithm, which means that the work we have to do is linear with respect to the size of the subarray in which you're partitioning. So here you have a subarray. So on the first level, you're partitioning two subarrays of size that is half of the original array. So you have 2 times 1/2 n. Here you're partitioning four subarrays that are size is approximately 1/4. So you have 4 times 1/4 n. And as it turns out, each level you kind of have to do n work. Every level you go down, you have to do n amounts of work where n is the size of the original array. So the total work you have to do in this case is n log n, theta of n log n. But that's assuming a best binary tree in which the binary tree is very bushy. It doesn't lean towards either side. But what if we have a very, very inefficient binary tree in which you just have nodes to the right? Well, this could also be a case that quicksort could encounter, in which all of the partitions are ends up falling in their first in the first in the first place of the array or the last place. So in this case we have it always falling in the first place. So every time we're not halving the size of our problem, we are only decreasing our problem by size by 1. So here we would have n levels. The tree would have n levels. So here, if we consider the total amount of work we have to do, going down each level requires n a linear amount of work with respect to n, and we have n levels, then the runtime will be n squared. So that's the worst case. That's the best case. So the best case would be n log n, and the worst case would be theta of n squared.